Rock and roll?
Yes, sir.
All right.
At the end of 10 minutes, I'm going to wave once, and 14 minutes.
Yeah, hold on.
Clock is clicking.
Don't start the clock yet. Even though he's going to give you time warning, that's for your information. We want you to complete your presentation so that if you did run over time, you know what adjustments you need to make.
For the final one. Yes,
You
sir.
follow what I'm saying?
Yes, sir.
All right. That's why we're doing a rehearsal, trying to fine tune the real deal.
Sounds good.
Start.
Good afternoon. Oh, good morning. My name is Jean-Paul Arbeza. This is Hector Di Donato, Alejandro Infante, and Nicola Lopez. We are Team 6. We are designing the striking mechanism for split Hopkinson pressure bar. We are working with the Air Force Research Laboratory in conjunction with FIU. They're the ones who are funding this project, the AFRL is. Now, the problem is that we need to implement a new striking system to an existing hobby bar. They ran this project last year, and the team made a functional hobby bar, but their striking system had some problems. The hobby bars are designed on one-dimensional stress wave propagation, and their striking system was a gravity-fed hammer, pendulum hammer, and that introduces more than one-dimensional stress wave, which is one of the requirements to have, so that did not work. Also, we needed to improve the data acquisition system because you need, since this is a dynamic stress characterization tool, you need to have high-frequency responses to catch the stress pulse running through the bar, and they were using too low of a frequency in their oscilloscope. Now, the reason for the hobby bar is because material properties change, such as yield stress and ultimate strength. They deform differently when they're loaded statically and dynamically. What we usually see in textbooks is static deformations. You pull something very, very slowly, it's quasi-static. You pull it very, very slowly, and you see when it deforms and when it breaks, the ultimate yield, the fracture, all those properties. But when you load them dynamically, if you grab a hammer and just hit it, it deforms at different points. It has a higher amplitude. But you can't get any data out of the hammer. So what somebody introduced was a split Hopkinson pressure bar. Now, the striking system we have designed, allows us to achieve the required velocities, to achieve the strain rates, the range of strain rates that we need to characterize these materials. And for initial sizing, since we are dealing with compressed gas, we needed to know the sizing of our capacitance reservoir, of our main supply tank, the length of the barrel, and many other factors. So what we use is this formula here. What this does is it takes the potential energy of the stored gas and it equals it to the kinetic velocity, the kinetic energy of the striker bar that we are shooting into our incident bar. Now, this is the final pressure times the final volume minus the initial pressure over the initial volume divided by the ratio of specific heats, the specific heat constant minus 1. Now that is assuming a calorically perfect gas, and we know some of the factors such as the minimum velocity that we need to obtain in our kinetic energy. We know our final and initial volume, and we know our final volume and pressure, so we can modify the initial volume. That is our only unknown. Now, for the data acquisition, we need to know the length of the stress pulse so that we know we're getting enough points in our data acquisition system, and that is determined by the length of the stress pulse T, which is proportional to 2 times the length of our striker bar divided by the sound speed in steel. And we determined that the minimum frequency needed would be 100 kilohertz.
So our design mainly consists of getting a 1/2 inch hardened steel rod down a barrel to obtain a minimum speed requirement of 100 feet per second. So if you think of it in a very vague concept, that you're trying to blow a very small rod down a very small diameter, and you come into a problem or a phenomenon known as choked flow, and this phenomenon is actually a loss in mass flow through a cylindrical pipe. And what that does in essence is limit how fast we could get the expansion of gas down a cylindrical pipe. So dealing with a 1/2 inch rod, we were very limited in the mass flow through the cylinder. So our design included a 1 inch diameter barrel, which as you can see is larger than the 1/2 inch steel rod. So what we did is, next slide. What we did is we had the 1/2 inch steel rod wrapped with a piece of Delrin spacer, which encompassed the entire inner diameter of the pipe and allowed us to increase the mass flow through the barrel, and was able to give us the final velocity of 100 feet per second consistently. That is just the barrel design. And then from the back, we have the 2-gallon compressed air reservoir, which is going to be holding nitrogen and going to be storing all our potential energy. The actuator is a fast-acting ball valve, which operates under compressed air as well, and we will be opening it with a solenoid valve, which with a flip of a switch opens that ball valve in less than a second and releases almost 2 gallons through that barrel. And we're also going to incorporate exhaust holes in the barrel, which allow the expanding gases to vent out and deaccelerate our striker bar to a constant velocity before hitting the Hopkinson bar. These are the exhaust holes that we were talking about. We're going to have them in an array around the barrel, and these exhaust holes, like I said, are going to allow the expanding gases to vent and allow the striker bar to maintain a constant velocity before hitting the Hopkinson bar. We also incorporated a series of sawhorses to have the entire project on a level plane that we could work at. And as you can see here, we have the Hopkinson bar on steel I-beams, and the gas unit, the compressed gun gas unit that we assembled on the same I-beam. This will ensure a linear shot, and that's our final project right there, final design. This is our schedule we have as of now. We started August last year, and we moved in towards this year, started our fabrication in around February, March, and we're right on time with our requirement schedule that we made up.
Okay, like John Paul said at the beginning, we're not only improving the striking system of the Hopkinson bar, but we're also improving the data acquisition and the results that you get from each experiment. The way you get results on this type of system is by getting voltage. Every time the bar gets deformed, even though you can notice it or you are not able to see it, there is a small deformation. And the only way to determine that deformation is through voltage. We're using Wheatstone bridges in order to get that voltage out of the strain gauge. The way Wheatstone bridges work is that, as you can see here in the graph, you have 4 resistors that they have the same capacity, the same value. if you put any voltage in, the way they are set up, if they are all the same, the voltage out will be 0. So if you put one string gauge, if you replace one resistor for one string gauge, you will have some difference in voltage. Now, every time that string gauge perceive any change in voltage, we can get the result of it. There are 3 ways to set up Wisdom bridges. There are quarter bridge, half bridge, and full bridge. They are pretty similar. The only difference is that on a quarter bridge, as you can see here, there is only one string gauge and 3 resistors. On a half bridge, you have 2 string gauges and 2 resistors, and on the full bridge, the 4 of them are string gauges. We decided to go with a full bridge since the string gauge are very sensitive, and they can perceive any small change in voltage. Even in our system, when we put the string gauges, they are on a very noisy environment. So when you see the readings on the oscilloscope, all you can see is noise. So the change of voltage is so minimum that it can be confused with the noise. So having 4 string gauges instead of 1 or 2, we can be able to have a more accurate reading in the change of voltage, since the 4 of them are perceiving this change. These are the string gauges. These are the small devices that we're using to get the change of voltage in our bars. The way the string gauges works is they have, as you can see in the picture, they have these small lines are connected all together. So if you bend a string gauge like this, these bars will get stretched and will get more resistance. And with more resistance, it means that they're perceiving more voltage, that they are changing more. So every time the bar gets hit, a wave, it goes through the bar, and it kind of bends the bar. So these string gauges can perceive this wave, and it can perceive the voltage is going through the bar at that moment. In order to stall the string gauges, it's the most, you have to be very careful, because working with string gauges, we can say that is the most, you have to be very careful, because it's where you can get more the wrong results. If they are installed wrong, you will be perceiving wrong voltages and wrong.
So where
results.
you're looking for sensitive, very sensitive.
You're looking for sensitive, and these gauges are very sensitive. They're even sensitive to the light, or to voice, or sounds, or anything. So the way you install these string gauges, you have to have a very clean surface. You have to sand it with different grades sandpapers. First, you start with a 400 sandpaper in order to remove all every dirt or everything that it can interfere on the readings. And after that, you go and you sand with a greater sandpaper. We can say 1,000 or maybe 3,000, which is a finer sandpaper, so it will leave a smooth surface on the bar. After that, you clean it with acetone in order to have it clean, and you have to make sure that when you're installing the string gauges, nothing touches the surface of the string gauge. So basically what you do is that after you open it, you put it on a special plastic paper, which is completely clean. You put it on top of it, and then you put a Scotch tape on top of the string gauge. Removing the plastic paper on the bottom, you place it on the bar. And after that, you gotta make sure that these two small cables, they don't touch the bar, since this bar has resistance and it transfers voltage. So you don't want to get that wrong message on the string gauges. So you just put some electrical black tape on it and cover it around and make sure everything's clean.
For the data acquisition system, we also use a conditioner. What a conditioner does is complete the width-tone bridge, so it simplifies the connections. They also have the resistors connected here, you can see in the picture. This conditioner also gives the voltage excitation into the strain gauges, and since, as he said, that we can read a lot of noise, one of the main purposes of this conditioner is to amplify the voltage output. So that way we can differentiate the voltage out of the noise. The gain in this type of conditioners is adjustable, so you can change it manually to the desired gain that you need. We're also using a Tektronix oscilloscope that is at 2 gigahertz per second. This oscilloscope is pretty fast, so we can store about 2,500 data points per pulse. And we calculated that our pulse length is going to be about 80 microseconds, so we need to be within that range in order to catch the data coming from the strain gauge. We're also using a tachometer and LED sensors in order to measure the speed of the tracker bar, because we need to make sure the speed that we got theoretically is in the coming out of that barrel. How these LED sensors work, they are set up in a mode that is called CCAP, that is a single capture mode. So when the bar passes through the first LED, it will turn on the timer, and when it passes through the second LED, it cuts off the timer. And in the internal memory, it will calculate depending on the distance from the LED, and it gives us the velocity in miles per hour. These are the data that we can get from the strain gauges. From the oscilloscope, we will see this type of graph that represents voltage versus time. The length of these pulses are calculated with the formula that JT mentioned before. And as I told you, this length is about 80 microseconds. And using a set of formulas and changing this voltage into strain and stress, we should be able to come up with this graph that is a stress and a strain for engineering purposes. The conclusion is that using this type of setup, we can get a more consistent reproduction of velocity and shooting, so we can repeat the experiment as many times as we want, and we should get the same results. Also, the diagnostic system upgraded. The frequency responses should be better, so we can read all the data points within that fast time frame. And the main purpose of this is to see the square wave, because when we see the square wave, we can see the deformation of the material. We just see less point, we're not going to see the square wave. And it's not going to be readable data. We need to thank our advisor from the airport, Joel House, Dr. Tansel from FIU, and a fellow graduate from FIU, and a graduate student from FIU.
Okay.